So gases and chemical reactions. When we have an amount of gas, either as a reactant or a product, we'll often specify how much we have in terms of its volume, temperature, and pressure, because mass of a gas is very difficult to deal with. So if we have volume, temperature, and pressure, we can use the ideal gas law to calculate the number of moles of the gas, right? And we did this in lab yesterday as well. PV equals nRT. I don't know why I expected the black stylus to write black. That's just surprised me. Sorry. So if we rearrange this for n, solve for n, we're going to divide by RT, and so we get that the number of moles of gas equals the pressure times the volume divided by the ideal gas constant times the temperature. Once you have the moles of gas, then you follow the same process as we did for other stoichiometric calculations. We use the coefficients from the balanced chemical equation to convert moles of this gas to moles of the other thing that we're interested in. So it's a variation on grams to moles to moles to grams. Let's do an example. In this reaction, 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver oxide decomposed? So here we have a chemical reaction occurring. Think stoichiometry. So we've got oxygen, and we're asked about another compound. That's a clue that there's stoichiometry involved here. So I'm going to use the balanced chemical equation to organize this information. 4.58 liters of oxygen. Well, I'm going to write that under the formula for oxygen. 4.58 liters. And then it's giving me a pressure and a temperature. I'm going to write those there as well. 745 millimeters of mercury, 308 Kelvin. Those are measurements that have to do with the oxygen. The question is how many grams of silver oxide. So question mark, and I want grams. Then we need a path, right? So our normal path is grams to moles to moles to grams. This is just going to be a variation. Here we're trying to find grams, and so we'll end with grams, and mole to mole is always there in the middle. But we're starting not with grams. We can start with moles using this information and the ideal gas law. Now, could you convert that to grams of hydrogen? Yeah. And then you could undo the conversion you just did to get back to moles. Hey, if that makes sense to you, and that's what you can remember, do it, right? The tortoise and the hare, the tortoise always wins the race because he's slow and steady and he knows where he's going. He doesn't get distracted. But we don't have a mass here, right? So instead of starting with the mass, we've got a pressure, a volume, and a temperature. And we can use that with the gas to find the number of moles. So here we've got volume and pressure and temperature. Are all the units suitable for the ideal gas law? No. The volume's good, the temperature's good, but the pressure's not in the correct units. So we do need to convert that to atmospheres. So that's multiplied by 1 atmosphere divided by 760 millimeters of mercury. So 745 divided by 760. So 0.980. That value has 3 significant figures. To avoid rounding, we're going to carry 2 extra digits, and the unit is atmospheres. So N equals PV over RT. N equals the pressure, 0.98026 atmospheres. times the volume, 4.58 liters, divided by the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin, times 308 Kelvin. So 0.98026 times 4.58 divided by, if you want to multiply those in the denominator, make sure you use parentheses. So divided by 0.0821 and divided by 308. And so we end up with 0.11, no, that's a 7. 177, there's our 3 sig figs, 54 moles. Moles of what? Moles of oxygen. Did you get that number from your calculator? Good. So now we have moles, we can jump into moles to grams. So I'm going to take moles of oxygen and I'm going to convert to moles of silver oxide, Ag2O, moles of O2 down there, because I want moles of oxygen to cancel out. And then I want to get to grams of Ag2O, dividing by moles of Ag2O. Units first. Mole ratio comes from the coefficients in the balanced chemical equation. 2 moles of silver oxide give us 1 mole of oxygen. So 2 moles of silver oxide gives us 1 mole of oxygen. And then for the molar mass of silver oxide, we need the periodic table. Silver, where'd you go? There you are. 107.9 times 2 plus 16.00. 231.8 grams per 1 mole. So I've got the 0.17754 times 2 times 231.8 equals, and we're still at 3 sig figs, 82.3, write down 2 extras, 0.7 grams, and then round that to 82.3 grams of silver oxide. Any questions? Yes?
I noticed on some worksheet problems, it seems like we should go in reverse, using stoichiometry first and then the gas law.
Yep,
Like
that
if
happens
they give you
too.
moles. Okay, so that's not wrong.
Not wrong, no. Because this question could be asked the other way around too. It could say, this 82.3 grams of silver oxide reacted, how many liters of gas were formed if this is the pressure and the temperature? So it's the same problem in reverse. Any other questions? So we have a set of conditions called standard temperature and pressure. These are abbreviated STP for standard temperature and pressure. Standard temperature is 0 degrees Celsius, or 273 Kelvin, technically 273.15 Kelvin, and 1 atmosphere. And these numbers would be exact, the 0 degrees Celsius and the 1 atmosphere. And why do we choose this as standard temperature and pressure? I think it's because this is a set of conditions that's very easy to attain. If you want a temperature of 0 degrees Celsius, you submerge whatever you have in a bath of ice water and wait a few minutes and it'll be at 0 degrees Celsius. So no technology involved. All you need is ice and water and you can get that temperature. And you don't even really need a thermometer. You'll know it's that. 1 atmosphere is easy because That's what normal atmospheric pressure is. So if you equalize the pressure in your container with the outside pressure, you're going to be at least very close to 1 atmosphere. So let's see what the volume of 1 mole of a gas would be at STP. So we use the ideal gas law to calculate this. We know that PV equals nRT. And to rearrange this to solve for volume, we'll divide both sides by P. Okay, so the P's cancel out. I'm going to just erase them because I can. So volume equals the number of moles times the ideal gas constant times the temperature divided by the pressure. Well, what's N? 1 mole, because we decided that we want to find the volume of 1 mole. So 1 mole, R is always the same, 0.0821 liter atmospheres per mole Kelvin. The temperature, see, if we used 0 degrees, if we did this in Celsius, we'd end up with a volume of 0, no matter how many moles of gas we use. So that's not cool. We always need to use Kelvin for these calculations with gases. So 273 Kelvin. The pressure is 1 atmosphere, so we divide by 1 atmosphere. So the moles cancel, the atmospheres cancel, the kelvins cancel. So you've got 1 times 0.0821 times 273 divided by 1. That would have 3 significant figures, and we get 22.4 liters. This is called the molar volume of a gas. The molar volume of an ideal gas at STP is 22.4 liters per mole. It's a very convenient conversion factor because it applies to any gas. Molar mass is specific to a compound or an element. Molar volume of a gas at STP is the same for every gas. Does that seem weird? It should. It is weird because things like that don't work with liquids and solids. The reason it works is because there's so much empty space between the gas particles that the actual size of the particle doesn't matter at all. So, you know, if you've got 10 people in the elevator, the size of the people matters, right? If you look at the people in the state of Wyoming, does it matter if they're all skinny little nothings or big, huge, bulky people? You know what the population of Wyoming is? It's about the same as Fresno.
Really?
Really? Without Clovis. Just Fresno. In an entire state. I remember that because we drove through there one summer. And you know, we're looking at the AAA guidebook because this was before cell phones. And I was like blown away. And as we're driving through there, it was nighttime, and we drove for miles without even seeing a farm light. I mean, there's just a lot of empty space. So with gases, just like the people in Wyoming, right, the size of the particle doesn't matter. And so the gas takes up the same amount of space no matter what it is. So 1 mole of any gas takes up 22.4 liters. So here we've got a mole of helium at STP, takes up 22.4 liters. The mass is 4 grams.
So should we know that number?
You should know that number, yeah, 22.4 liters. You could calculate it pretty easily too. 1 mole of gas at 1 atmosphere, 273 Kelvin. But that's a really good number to know. Looking at a mole of xenon. Xenon atoms are much larger than helium atoms, but they still take up the same volume because of all the empty space. They weigh more though, 131.3 grams. So this 22.4 liters is going to be a lot heavier if it's xenon than if it's helium, but it's going to take up the same amount of space. So the molar volume, the 22.4 liters per mole is a great shortcut when you're doing calculations with gases. So here's another gas stoichiometry problem. How many liters of oxygen at STP are required to form 10.5 grams of water? This at STP is our clue. We can use the shortcut. So again, use the equation, the chemical equation, to organize the information. Here we've got 10.5 grams of water. The question is, how many liters of oxygen? So question mark, liters at STP. So normal path would be grams to moles to grams. Here, when we look at what we're given grams information about water. We're asked question mark liters about the oxygen. So we're starting with grams this time, grams to moles, but we're not going to end up with grams. We're going to end up with liters at STP. Now, could you use the ideal gas law to go from moles of oxygen to liters? Yeah, plugging in the standard temperature, the standard pressure, you could do that. Or we can just use the 22.4 and it's simpler. Okay, so grams, 10.5 grams of O2. So I'm going to convert that to, no, not O2, H2O. Convert that to moles of water, grams to moles of O2, to liters of O2.